Okay, welcome back everyone. The next speaker is Bas Janssens from TU Delft, and he will talk about localization for positive energy of gauge groups.
Thank you for the introduction. And first of all, let me thank Barbara and Francesco very much for organizing this conference in difficult circumstances. We really appreciate it. Great. So now that I've thanked the organizers, that's a good moment to ask how much time I have. It's now 10 past, right? So until 4:05? Fair enough. So this is joint work with Carl Herman Neep. I've been talking about this line of work for at least 8 years. And this is the first time where I can actually point to a preprint which appeared on the archive last week. So now you can actually read what it's about. Okay, so let's start with the setting. So we start with a manifold with an R action. And we think of this R action as the time flow. So you might want to think of this manifold as a space-time manifold. So over this space-time manifold, we have a principal bundle, say a principal K bundle. And we're going to assume that K is, well, say a compact, simple, one connected Lie group. Each of these three items can be relaxed. So this is just to keep the presentation as simple as possible. Simple can be relaxed to semi-simple, but compact abelian is not included. So that's something you would want in gauge theories, but that doesn't work. We are also going to require that this R action on your manifold lives to an action by automorphisms on the principal bundle. Which means I can differentiate connections, sections, etc. in the time direction. Okay, so in this context, yes. So in this context, the gauge group is a group of vertical automorphisms of this principal bundle. We're going to think and compactly supported. You can also view them as sections of the adjoint bundle. So this is a locally complex Lie group. And it's modeled on the gauge algebra. My convention is that the big add, what you get if you kind of glue the group, the principal bundle, using the conjugate action. And the small add is a bundle of Lie algebras you get by adjoining the Lie algebra of this parameter. Okay, so we introduced some interesting Lie groups, Lie algebras. I'm interested in projective unitary representations. So let's call this the algebra big G, the group big G, and this the algebra factor G. So then a unitary representation would be a homomorphism, zero representation from your group into the group of unitary operators, some Hilbert space. I'm interested in projective unitary representations, which means I would like to consider homomorphisms from your group into the group of projective unitary transformations of your Hilbert space. So unitary operators up to a constant, a non-negative constant. Okay. This is a very general question. Let's make our life a bit smaller. I'm interested in projective unitary representations, which are smooth and of positive energy. Positive energy is a word which takes up a lot of space on the blackboard. I'll use it quite often, so I'll abbreviate it. Okay, so this smoothness assumption is it's a technicality. It's a reasonable assumption. You expect it to be satisfied for interesting representations. For finite dimensional, the algebra smoothness is equivalent to continuity with respect to the strong topology on your unitary group. So that's what you read about. For infinite dimensional Lie groups, it's a slightly stronger assumption. I'll need it when I come to the proof of the main theorem, but let's leave it for now. Okay. This second bit here, the positive energy condition, that's the real constraint. That's a serious condition. Is this better? Also online, is this good? So please, people online, do object if you cannot hear.
Okay, we will.
Thanks. So let's start with this positive energy condition. So a projective unitary representation is of positive energy. If it extends to a projective unitary representation, which I'll also denote by var1, not of the gauge group itself, but on the semi-direct product into real numbers. So on the Hilbert space, you represent not just the gauge group, but also the time translations in a reasonable way, in a way that interacts nicely with your gauge group. And this has to be in such a way that if you restrict attention to the time restrictions, so if you just look at the time translations do, well, then of course you get a one parameter group of projective unitary transformations. You can always represent it by a group of unitary transformations, a strongly continuous one. And that has a generator. And the generator of time translations on a Hilbert space is usually called the Hamilton operator. You can interpret it as an energy. So this positive energy condition means that you can extend this representation in such a way that this Hamilton operator, which is automatically and essentially self-adjoint operator in the Hilbert space, require that it has a positive spectrum. or at least the spectrum which is bounded from below. The spectrum of the Hamilton operator, you might want to think of that as the energies that can. So this is the most important restriction we will put on the representations that we're looking for, and I'm claiming that under this restriction we have very strong classification.
Can be chosen to be 0?
Yes, you can choose the bound to be 0. So the thing is, the unitary group which represents your projective unitary operators, you can choose it at will. So you can always multiply it by e to the power t times e0 and get rid of the 0 energy.
May I ask a question, please?
Of course.
I'm very disturbed by your assumption of smoothness of the representation, because an infinite dimensional unitary representation is never smooth. It's only smooth if you go to the sub-representation of smooth vectors.
That is precisely what I'm going to do. Thank you for that question. I hope to reassure you that it's a harmless condition.
But look at L2 over a Lie group with the left translations. If a function in L2 is not smooth, then the action of the group is not smooth in the Hilbert space.
There exist counterexamples, I agree.
Yeah, but this is general. Every infinite dimensional unitary representation of a finite dimensional Lie group is not smooth unless you go to the sub-representation of smooth vectors, which is a representation in a Frechet space only. And you have also...
A definition of smooth will be that the space of smooth vectors is density of the space. Does this really...
that's your definition.
It didn't give the definition. I don't have to skip it until after it. But I'll come back to it.
Okay.
Yeah, so for finite dimensional Lie groups, this is automatically satisfied by Göring's theorem. But since we do not have a Hahn measure, we have to require it for infinite dimensional groups. This is as high as I can go. Okay, so the main result I wanted to talk about today is the following localization theorem. So this is joint work with Cattafi. And it says the following thing. Suppose that the R actional and is fixed point free. So time does not stand still, if you like. Then for every projective positive energy representation, so that is a representation group of compactly supported sections on your manifold with values in the adjoint bundle of a principal bundle. So now to the projective unitary representations, the projective unitary group of your headings. For every such representation, there exists a one-dimensional closed embedded submanifold. It's called an S, which is R invariant. Such that the representation factors through the evaluation of this submanifold. So the submanifold determines what happens, and the rest of the H group is irrelevant. So if you have a gauge transformation, you can restrict it to a one-dimensional submanifold, and there exists a representation of this group of gauge transformations on the one-dimensional submanifold, and that determines everything. So the upshot is that if you consider positive energy representations of your gauge groups, then one-dimensional base manifolds is the essential case. Nothing else can occur. Disappear. And this is good because we understand representations of gauge groups over one-dimensional manifolds fairly well, at least as those manifolds are closed. So one consequence of this is that we get a complete classification in the case that the manifold is compact and that the R action is fixed point free. Let me explain in a picture. So suppose we start with a compact manifold. So draw a torus again, something like this. And we need an R action. So say the R action is rotating the torus. Then it tells us that for every projective unitary representation of positive energy for the gauge group of this torus, of this compact manifold, there exists a one-dimensional R equivariantly embedded submanifold. Well, if it's a closed embedded submanifold of a compact manifold, it has to be compact as well. Nobody says it has to be connected, so it's a disjoint union of circles. Each circle would be an orbit for the R action. The R action is like this. You just have finitely many orbits. Circle. And the gauge group over a circle is a loop group, or actually a twisted loop group, because we're looking at a principal bundle over a circle. And we have an R action that leads to the principal bundle that gives us a connection. And this connection has holonomy. So this holonomy gives you a twist if you go around, and you actually have a twisted loop group. Representation theory of twisted loop groups is very well understood, and the positive energy representations of twisted loop groups, that's more or less the same as highest weight representations of affine Cattafi algebras. Those are given by a dominant integral weight, which is the highest weight for the highest weight representation. So what is our classification of the representations? So first we pick a collection of finitely many circles, and then we decorate each of these circles with highest weight, which is a discrete data, right? It's just a set of integers. This looks a bit like this decorated Riemannians that Cornelia was talking about. The only difference is that now the embedded submanifolds have to be R equivariant. Okay, so this is a consequence for compact manifolds where the R action has no fixed point. For non-compact manifolds, we have a picture which is slightly less complete, but still quite advanced, I would say. So there are two things which change. First of all, you can have infinitely many connected components of your one-dimensional manifold. Secondly, those components can be either circles or real lines. The fact that you can have infinitely many connected components that we can kind of handle, we need some C-star algebra theory for that. So the description is not quite as simple as that. So you have infinitely many circles, you have to decorate them with extra data, and then there is a certain state of a UHF C-star algebra that you need to complete the picture. Real lines are more difficult because kind of the gauge group of complex or the gauge group on the real line is something like the pointed loop group, and the representation theory of pointed loop groups is far from being understood. That's a partial results. Maybe before I move on to the proof of the theorem, one more consequence I wanted to mention, and that's kind of the motivation for doing most of this work. The picture, yes, it seems to fit. Maybe another consequence. We could look at conformal compactifications of Minkowski space. So let's do it for two-dimensional Minkowski space for two reasons. One reason is that two dimensions comfortably fit on a blackboard. Another reason I'll get to when I finish talking about this. So let's start with two dimensions. How does two-dimensional Minkowski space look like? Well, we have one space dimension and one time dimension. What does the time translation do? Well, it fixes space and it moves time, right? So that goes up. What happens if you look at the conformal completion of Minkowski space? Then you kind of move in the light direction to the right upper or the left upper side, and then you apply a hyperbolic arctangent, or I think an arctangent actually, and then you kind of move infinitely closer. So you get this picture. Time kind of moves up space. Now we have shrunk R2 to fit into a neat little square. We've done so in a conformally invariant way. This is what people sometimes call a Penrose diagram. And here, well, time moves a bit like this. This point here is where you end up if you're at the origin and you let time flow to infinity. This is cool. Future time-like infinity. Then you have past time-like infinity. This is where you end up if you kind of stand still and go back in time. And then if you fix time and you let space go to infinity, you end up at space-like infinity. So what are all these points? They're they're called like infinity. It's where you end up if you kind of move along a line. And you can do that starting at different points, you'll end up at different points. So this is the conformal completion. You can also consider the conformal compactification. And that's what happens if you take this Penrose diagram and you fold it up into a torus, right? So you glue this side to this side and you glue this side to this side. So what you get is a torus. And the boundary of this square, which is essentially null infinity, it becomes two circles. So we have a nice compact manifold. We would like to apply our theorem. There are some subtleties. One subtlety is that there is obviously a fixed point, right? So fixed point 3 means that time does not stand still, but at future time infinity, I mean, obviously you can't go further into the future. So this point here is a fixed point for the R action. So this point at infinity, so we've identified all kinds of space and time-like infinity that we have. Is a fixed point. But luckily we proved our theorem for a non-compact manifold, so we can simply remove the fixed point and apply that. Let's call this the two torus, and we take this two torus and we remove. Another subtlety is that the context of Minkowski spacetime, you don't just have one time dimension. You don't want equivariance just with respect to a time action, you want equivariance with respect to the Poincare group. So you can actually implement that. It's not so easy to kind of take the theorem that I wrote on a blackboard and kind of replace the real numbers with the Poincare group. And what you'll get is essentially the same theorem, except that this one-dimensional submanifold has to be invariant under the Poincare group. Okay. So what does the Poincare group do? Well, it acts transitively on R2, obviously, because it contains translations in both the space and the time direction. Okay, so everything except the red lines is a two-dimensional orbit, and the only one-dimensional orbits are the two red lines. So the result we get is that the energy representations of the gauge group all compactified Minkowski space. We factor through well, the values of your gauge transformations on these two red lines, which you think of as null infinity, kind of the limiting value of your gauge transformation if you go to null infinity. And well, germs at this point, we cut our point out of the manifold, so we don't know anything anymore. What you can do, and this is work in progress, you can put the point back in, and then you can do quite a lot of work actually, and then you can prove that you don't really have to look at germs, you just have to look at two jets, derivatives of degree 2. Okay. It's a nice result, I think. And And so one reason why I did this for R2 is because they are in the conformal boundary that you have one-dimensional pockets. And you get the picture you kind of expect from conformal field theory, right? So you have one circle that represents kind of your homomorphic sector and one circle that represents your anti-holomorphic sector. And you have an extra thing, which I haven't seen in conformal theory field theory books. And that's presumably because these representations are not conformally invariant. They're just Poincare invariant. It's new as far as I know. Any questions so far? So this was as much as I wanted to say about what the main theorem is and what you might expect to do with it. But for this audience, it would be nice to actually talk about the proof of this theorem. This is not something you get to do at every conference. That's a lot of water. We already discussed smooth representation a little bit because of Riemannian's question. So I think it's good to at least have the precise definition on the blackboard, because the condition is really needed to go from representation theory of Lie groups to the algebras. So what it means is the following. So suppose we have a projective unitary representation, then an array in your projective Hilbert space is called smooth. If the orbit map is smooth, so that's the map from your group to your projective Hilbert space, which takes your group element to your group element, acting on the projective function. So let's denote the set of smooth rays by pH infinity. You can actually prove, this is not hard but also not trivial, that this is again the projective space of the subspace of smooth vectors. And we define the projective representation rho to be smooth. If this space of smooth rays is dense. So maybe for Peter, is this a reasonable definition?
Yes, okay, I agree, you can.
I spent some time trying to motivate this definition, but we can skip this because Peter said it is okay. So it's equivalent to continuity with respect to the strong topology of the unitary group. If your group is finite dimensional, if your group is not finite dimensional, you can find counterexamples, but I mean, people really, for example, Daniel Delft wrote a paper where he constructed a counterexample. So you have to look for counterexamples if you want. So what does this condition do for you? Well, it makes it easy to go back and forth between projective unitary representations group G, if they are smooth, and just smooth representations without projection. This representation rho bar, and it's called the representation itself rho. And then the price you have to pay is it's not a representation of your Lie group, but of a central Lie group extension. You write the word in red because that's not entirely trivial. And so getting this group is easy. You have a projective unitary representation into representation of your group G into the projective unitary group of your Hilbert space. The projective unitary group has a natural central extension, the unitary group. Okay, you just pull it back. And because this is a central U1 extension, this will be a central U1 extension as well. And because these are topological groups, these will be topological groups as well. So the content of the theorem is that this guy will not just be a topological group, it will be a Lie group. You have to work a little bit together. Since it's a Lie group, you can take the Lie algebras of all these guys. And you get a central extension of Lie groups. And given a smooth representation of a Lie group, you can always differentiate and get a representation of a Lie algebra. We denote it by D rho. And D rho will be a representation of the space of smooth vectors. So these operators D rho of xi is a Lie algebra element. They will be unbounded, essentially self-adjoint operators. And this space of smooth vectors, it will act as a common core for all of them. In particular, commutators between these unbounded operators exist, which is not interesting. Okay, so this is what the smoothness assumption does for you. In particular, you see that if you start with a projective unitary representation, you obtain a sample extension of a Lie algebra. And sample extensions of Lie algebras are classified by second Lie algebra cohomology, as Lucas explained. So in particular, if you start with projective unitary representation, which is you end up with, say, something like a 2 cosine. A 2 cosine is something which eats 2 Lie algebra elements, spits out a number, and it satisfies some Jacobi-like algebraic relations. What happens if you split this sequence and then take the Lie bracket and project? Okay, so for the proof of the theorem that I just explained, this localization, these 2 co-cycles are really the starting point. So let's try to have something like a sketch of a proof. These 2 co-cycles, like I said, those are kind of the oxygen. That's what this start with. So the first step is that you realize that all of these guys are given as follows. So 2 co-cycle is something which eats 2 Lie algebra elements. The algebra elements are sections of your hadron bundle. And it spits out the numbers. How do you construct this number? You take the section, You take a killing form acting on your section at a certain point and the t of another section. Okay, to take the differential, you need a Lie connection. You can choose any one you want. If you take a different connection, you'll get a different co-cycle, but it will be the same class. So for the cohomology, you can just fix a connection if you want. So this is a section with values in the adjoint bundle. This is a one form with values in the adjoint bundle. You apply the killing form to the vertical thing somehow. So this killing form eats all the algebra data, and what you're left with is an almost one form. Right? Just a one form on the left. And if you have this one form, you have to make it into a number. So you have to apply a current. And you want this current to be closed, which is to say that it has to be 0 on the element. And this closeness of the current, of course, makes the co-cycle identity, or at least for the anti-symmetry. Okay, so this is a way to construct co-cycles. The co-cycle you get depends on the connection and the closed current. The class you get does not depend on the connection, but it's really determined by the current. So this is how this isomorphism works that you guys had in this talk. So here's the thing: if you have a positive energy representation, then with a small lemma, you can show that this current here really comes from a measure. And for distributions to be measures, you need some positivity condition. Right? So this positivity condition is kind of provided by this positive energy condition. Let's call this measure B. It's a measure on your manifold downstairs, and it's an R invariant measure. Okay. So actually, if we start with a positive energy representation, the co-cycle looks like this. We take the killing form, apply it to psi, and actually use the letter D for differentiating in the time direction, which we can do because we have a lift from kind of the time vector field to the principal bundle. So this gives you a function, and you can just integrate this function over the manifold using your measure. Okay, so this is nice. We started with a positive energy representation, and we end up with some measure on our manifold, which is R invariant, and which is there apparently. It has to do something. Incidentally, so this is in the positive energy setting. If you require KMS representation, then Milan, who is here in the audience, proved a similar result, but which generalizes this. Okay, so what does that do for you? Using this, you start with a Cauchy-Schwarz type of estimate, which tells you something about your Lie algebra operators. It tells you that your Lie algebra operators can go skewer joint. If I multiply them with I get essentially self-adjoint operators. They're unbounded. But the Cauchy-Schwarz inequality tells you that these operators are somehow small with respect to the Hamilton operator. So more precisely, if you take the expectation of this guy, then it is no more than twice the expectation of the energy. Not quite that. This measure has to function, enter in, but this measure enters in as a number, namely the L2 norm of your psi. Actually, here xi has to be a derivative of something. And take the L2 norm with respect to this measure. So these are unbounded operators, but they're somehow not too big. They're controlled by the average energy and the L2 norm of your section. This is very simple to prove. I'll skip it, but now I can actually refer to the preprint on the archive. It's like 9%. But it already has a nice consequence. I mean, if you have a section with the property that the support of the xi, if that has measure 0, then it can't do anything on the Hilbert space. How this measure really controls what your representation is doing. So the rest of the structure is this proof is trying to show that this measure has support which lies on a one-dimensional segment. And then
There is a question online.
please go ahead. It's a good time.
I missed
Oh, no,
it,
sorry.
sorry.
It was a mistake.
No question?
Nope.
Okay, thanks. Okay, the next thing we're going to do is to use this control that the measure gives us over the representation to prove a continuity property of your representation. So what you prove is that so you start with a Lie algebra representation. Well, and with values in little at p, the Lie algebra. You take a central extension. You map them to anamorphisms, it's not quite of your Hilbert space, but of the space smooth vectors. What one would like to know is that this extends to a space of sections which is a bit rougher than smooth. So we want to extend that to something like Sobolev, H1 in the timeline direction, and just L2 in the direction transversal to time. Call it H1 delta. So you prove that there exists an extension of this representation. So this space is, you should think of it as in the time direction, you have Sobolev H1, so you have kind of one derivative in the time direction in your norm, and you just have L2 regularity measurable, so to speak, perpendicular to the time direction. So this is the closure of your compactly supported smooth sections with respect to a norm which looks something like the L2 norm plus the L2 norm of one derivative, but this derivative is only in the time direction, not in the space direction. And if you want to be really precise for technical reasons, you have to replace this measure by another measure, which is slightly larger, but it's still R invariant, and it is absolutely continuous with the previous. So on compact submanifolds, you might think of these as the same measure. Okay, so we can prove that our Lie algebra representation extends to a representation of a larger Lie algebra. And here comes the point. We can even prove that on a slightly smaller subalgebra, which involves two derivatives in the time dimension. We have a dense set of analytic vectors. And having a dense set of analytic vectors is nice because these are locally exponential Lie groups. And if you have a dense set of analytic vectors, you can integrate these Lie algebra representations to the group level. So we don't on this slightly smaller subalgebra with two derivatives in the time direction, we can integrate to the Lie group level.
That's why you mentioned two jets only, isn't it?
It's a slightly different story, but it's related to it. So it's, you're using the same techniques, yeah. But there's for prime jets.
And sorry, what's the topology on H infinity? I never asked you about H infinity. What's the topology of this?
The topology on
Smooth space. H infinity. Smooth space.
on H infinity. Let's see. It's certainly a barreled space. I think it's even a Fisher space, but I don't need the topology so much. Somehow the continuity is on this side, right, with respect to the pointwise topology. That's what I need in order to integrate. Okay, so why do I care about having group representation so much? Because it really restricts the possible co-cycles that can occur. And these co-cycles, they are associated to measures. So somehow, if I can restrict the co-cycles that can occur, I can restrict the measures that can occur. And that's precisely what I want to do. I want to prove that the measures have to kind of live on one-dimensional submatrix. Okay. So what do I do next now that I have these results? I choose a flow box. It's like my manifold. So since my flow is fixed point free, I can just rectify the flow with a small cube if you want. So U0 would be the base of the cube, and this interval I would be the spectrum time. And then, because I can handle sections which are only L2 in the perpendicular direction, I get a Lie algebra inclusion. Functions on an interval compactly supported with values in my fiber Lie algebra into this Lie algebra of sections of which I know that it integrates to the group level. So what I have to do is I have to choose some subset E, a magical subset of my base, so to speak. And what I do is, I take a function and I happens to the function multiplied with the indicator function in the space direction. Compactly supported function, and I map it to a compactly supported function on the square, which kind of does what this function does everywhere, and then it suddenly kind of turns 0. This is a continuous Lie algebra homomorphism with respect to the topology, which has 2 derivatives in the time direction and 0 derivatives in the space direction. That's the main point. And then I'm almost done. So I know that I can integrate this guy to the group level, which means that I can also integrate this guy to the group level. I get a projective representation of a Lie group, which has this guy as a Lie algebra. And those are, well, essentially loop groups, right? So loop groups with a point cut out of this group. At least the central extensions work the same. So I know that if I integrate this guy to the group level, I get a cocycle, which looks like this. It's just the integral over I of f times some constant. And this constant is important. It's called central charge of the representation. And it depends on the measure, right? So you can show that this central charge is 2 pi times the measure of this measurable set. Well, actually, this measure is a measure which lives here, tensor the measure dt. So I can write this as some measure of u0 applied to a measurable set. So this is the central charge. And we know that if these representations extend to the Lie group, then this central charge has to be an integer. That's essentially due to the fact that these cocycles, you can consider them as the curvature of a connection on your central extension, considered as a principal circle. This guy has to be an integer for every possible measurable set that I put into it, which means that this measure has to be a sum of delta functions. And this was a measure on the base. So the measure on the base is a discrete sum of delta functions. And this measure is just dt. And that means that your measure on the whole manifold has to be something like, which locally looks like some integers times delta x tensor dt. And globally, that means that your measure concentrates on an embedded sub-manifold, which is invariant and different. And that's what we want to do. So that's a sketch of the differential. Thank you very much for your attention, and excuse me for going over time a few minutes. If there are any questions, then I'm happy to answer them.
Any questions maybe online first? In presence? Okay, then let's take Bas again.